Hello everybody, and greetings from the Delta College Planetarium. My name is Brian, and I'm here to bring you the next episode in our continuing series about the constellations. Last time we looked at Cassiopeia, the queen of ancient Ethiopia and the mother of Andromeda. Today we'll search for Cassiopeia's husband, King Cepheus, also among the stars of the northern circumpolar sky. Both Cassiopeia and Cepheus are visible all year round. In fact, they never set, but during the autumn they are high in the sky and easy to spot. Cassiopeia is relatively bright and shaped like the letter W. Because of its distinctive shape, Cassiopeia is particularly easy to see, and with practice, many stargazers will be able to pick Cassiopeia directly out of the sky as they can with the Big Dipper or the Summer Triangle. The W shape of Cassiopeia isn't symmetrical. One side is shallow and the other is sharp. Look at the sharp side of the W. Draw a line connecting the point of that side of the W to the last star in Cassiopeia and extend that line out. That line will lead you to this relatively dim star. It's not particularly noteworthy. You might pass right over it. The only distinctive thing about it is that it's part of a group of 4 stars of about the same brightness that make a box. A 5th star adds a triangle on top. It looks a little like a child's drawing of a house. This is the constellation Cepheus, the king of ancient Ethiopia. It's usually depicted representing the king sitting upon his throne, but most people tell me they see a house or a church steeple in these stars. Cepheus is a relatively dim and difficult constellation to see. It is certainly harder to spot than neighboring Cassiopeia. It is a lesser-known constellation, and frankly, nobody ever comes to the planetarium asking to see Cepheus. Despite that, Cepheus contains one of the most important stars we've talked about, a star that helped us understand our place in the universe. Delta Cephei is not particularly bright. At about 4th magnitude, it's easily overlooked. In 1784, the English astronomer John Goodricke observed that Delta Cephei varies in brightness. It brightens from magnitude 4.4 to magnitude 3.5, and then dims back to 4.4 over a little more than 5 days. If we take careful measurements of a star's brightness over time, we can observe the star's light curve. Delta Cephei's light curve is a smooth, continuous transition. There's no indication of anything passing in front of the star, like a second star or a planet. Knowing that the curve is varying smoothly, you might expect it to look something like a sine wave, gently varying between its peaks and troughs. But when we observe Delta Cephei, we don't see that. Its light curve looks more like this, a sawtooth pattern. It gets bright very quickly and then slowly dims out, only to brighten again. What's going on here? This is what astronomers think is happening to Delta Cephei. The star's outer atmosphere has a lot of helium in it, and helium has the unusual property that as it gets hotter, it becomes more opaque. The light and energy of the star has a tougher time moving through the outer atmosphere. The energy becomes trapped and transfers heat to the atmosphere. Heat causes gases to expand, so the outer layers of Delta Cephei puff up. As a gas expands, it loses heat energy. The atmosphere cools down. As this helium-rich layer cools, it becomes more transparent, and the light and heat of the star are free to shine through unobstructed. The star looks brighter, but gravity starts to pull the outer layers back down, and this collapse increases the heat of the atmosphere. Heating it up causes it to become more opaque, dimming the star and trapping its heat, until it rapidly expands once again, and the whole process repeats. Careful examinations of the light curves of other variable stars sometimes yield the same sawtooth pattern of variation, indicating that those stars are also undergoing periodic pulsations like Delta Cephei. The stars producing light curve patterns like this are called Cepheid variable stars. In 1908, the American astronomer Henrietta Swan Leavitt was studying Cepheid variable stars in the Magellanic Clouds, dwarf galaxies that orbit the Milky Way, when she made one of the most important discoveries in astronomy. Leavitt made the assumption that all of the Cepheid variable stars observed in the Magellanic Clouds were roughly the same distance away. There was no way to know precisely how far away any of those stars were, but the Magellanic Clouds were thought to be so far away that being on the far side of one isn't very different from being on the near side. Leavitt found that in the observed Cepheid variable stars, the time it takes the star to cycle from bright to dim and back is related in a predictable way to how bright the star is. The brighter the star, the longer the period of variability. This relationship established a relative way to compare Cepheid variable stars. If two stars had the same period, but one was only 1/4 as bright, then we could deduce the dimmer star was actually twice as far away. This is incredible. It's easy to measure the period of variation. We just watch the star. If we do that, now we know exactly how bright it compares to other Cepheid variables. If we knew the distance to just one Cepheid variable, then we could figure out how bright it is in an absolute way. And we could use that knowledge to figure out how far away any Cepheid variable is. Fortunately, there is a Cepheid variable close enough to Earth that we can measure its distance in other ways, like using parallax. Delta Cephei. Henrietta Swan Leavitt discovered a way to compute the size of the universe. In 1924, Edwin Hubble located Cepheid variable stars in the Andromeda Nebula. Using Leavitt's relationship, Hubble showed that the Andromeda Nebula was a separate galaxy on the order of millions of light years away. There's no way John Goodricke could have known in 1784 where his notes would lead. The simple observation that a star changes brightness leads to the discovery 125 years later of a relationship between the variation of a star and its brightness, which in turn, 20 years later, leads to the realization that the universe is so much greater than we imagined. That's how science works, building upon the work of previous generations to extend the boundaries of human knowledge. Discoveries that seem unimportant or even useless today might change our understanding of the universe in 100 years. There's no way to know which of our investigations will lead to great discoveries. We must look everywhere. So if it's clear where you are tonight, go out and look for Cepheus. And take a moment to appreciate how the change in brightness of just one of those stars led to knowing just how big the universe really is. That's it for today. Next time we'll examine another constellation. This is Brian from the Delta College Planetarium, wishing you clear skies.